Take a look at current density, symbolized by the letter J. I know that the current density is equal to the current over the area. This is if it's uniform, or if it's not uniform, then we do a differential, di dA. Suppose that if we think about it, if I have a wire here with current flowing through, if the location does not matter, then it's uniform current density, and we're just dealing with this. However, current tends to flow much better in the middle than it does on the edges, and so what you're more apt to see if this is a wire is that the closer you are to the middle, the better the current flow is. And so if I have some relationship here of, let's say that my current density is equal to 5 amperes per square meter times my radius, let this be 2 millimeters, 0.002 meters, so 0.002 meters minus r, which is the distance from the center, squared. And so when little r is equal to big R, then my current density is 0. In other words, this is the point when the way this is set up is that there is no current flowing right on the edges, and that the current flow is the greatest when r is equal to 0, and then we'd have 5 times 0.002 squared. That would be the current density. But I want to figure out what is the total current flowing through the wire at this particular point. And so, well, it's not a uniform current density, and so this is what we're working with right here. So di is equal to j dA, or my current is equal to the integral of j dA. Well, j we have a formula for, I gave it to you, so that's the integral of 5 times I'm just going to put big R for right now, the R, times dA. Well, I know that area is pi r squared, and so dA is equal to 2 pi r dr. And because of the symmetry, if we look at it head on, so we're looking at it straight in that way, and we're basically looking at d area right here. This is radius r, little r. So that's d area, not Alcoholics Anonymous. Then if I cut this right here and sort of stretched it out, the length of it would be 2 pi r, and the thickness of it is just the differential of r, because we're at some r here, some r there. There's just an infinitesimal small difference between the inside and outside of this annular cylinder, or circle, however you want to look at it. And so another way of finding dA. So this becomes, and that was squared, and this is 2 pi r dr. So let's pull the constants out. So this is 10 pi times the integral of r minus little r squared r dr from 0 to big R. And now it's just a simple square the binomial, multiply times r, and take the integral. So let's do that. So I have my current is equal to the integral, so it's 10 pi on the outside, 0 to big R, r minus little r squared r dr. And so this becomes 10 pi integral from 0 to r of r squared minus 2 big R little r plus little r squared times r dr, which becomes 10 pi times the integral from 0 to r, multiplied out, r squared, or distribute it, r squared r minus 2 r squared plus r cubed dr, which is 10 pi times, this becomes 1/2 big R squared little r squared minus 2/3 big R little r cubed plus 1/4 little r to the 4th from 0 to big R. And we've got 10 pi times, that should be meters to the 4th power. I get 1/2 big R to the 4th minus 2/3 R to the 4th plus 1/4 R to the 4th. And so obviously there's an r to the 4th there. So then I'm left with 1/2 plus 1/4 minus 2/3. So 1 So that's basically 3/4 minus 2/3. And we could go decimal, but let's stick with the fractions just for fun. Looks like 12ths the common denominator, so I have 9/12 minus 8/12, which is 1/12. So I'm left with 10 pi over 12 r to the 4th power. And so 5 pi over 6 r to the 4th. And then we can stick in numbers. Recognize that the units here are amperes per meter to the 4th. And so this would be meters to the 4th. We'll cancel out, and I'm left with amperes. And I believe, yeah, big R is 0.002 meters. So we can actually come up with a real value here. And I get 4.189 times 10 to the negative 11th amperes. So that is the current flowing through that wire.